Hello and welcome to lecture 3 of the course Theory of Computation. So in the past 2 lectures we saw the brief overview of the course, and then we saw what are alphabet, symbols, languages, etc. So today we are going to start off by examining the first model of computation that we will see during the course, which is called deterministic finite automata. Before that, just want to remind ourselves about the definition language. The language over sigma, where sigma is an alphabet. It could be binary alphabet like say 0, 1, or English alphabet like A, B, C, D up to Z. Right? A language over sigma is a set of strings over sigma, or in other words, it's a subset of all the possible strings constructed over sigma. So a language is a subset of sigma star, right? So language A is a subset of sigma star, right? So we saw some examples such as set of all the binary strings with an odd number of ones, set of all the binary strings with an even number of ones, set of all the binary strings that end with 0, set of all the binary strings that are palindromes, set of all the English words that contain the letter A, right? So these are all languages over the respective alphabet, right? Right. So just with that reminder, let us move on to finite automata, right? So just one small thing before we get to the definition. So we'll be seeing various types of automata during this course. And just to remind everybody that the word automata is plural, right? A-U-T-O-M-A-T-A, and the singular is automaton. But while speaking about automaton or automata, I may not be able to make the distinction or use the plural or singular accurately. So this is the distinction. Automaton is a single device and automata is a plural. Okay. So finite automata are basically computational devices or computers which have a limited amount of memory, okay, and basically the memory is obtained using the use of states, okay. So for instance, we may have timers on, let's say, stopwatches, or even mechanical devices that are timers that measure a certain time. We may have thermostat, like if you recall, let's say a room heater or a water heater in our respective houses will have what is called a thermostat. So the goal of the thermostat is to maintain the temperature of the water in the water heater. Let's say it has to maintain at 50 degrees Celsius. So it will heat the water up to maybe like 52 or 53 degrees Celsius and then turn off the heating, right? So the water heater will now, it's supposed to be an insulated device, but it will slowly start losing temperature because no insulation is perfect. And once it maybe drops below 50, the thermostat comes on again and starts heating again. So basically there are 2 stages. One is to heat and one is to stop the heating, right? So this is also an example of a state-based device. Another one could be an automatic door opening closing controller. Right. So, like you would have seen this in a lot of newer buildings where as you walk up to the shop, there will be some glass door or something that automatically opens, and after you have entered and nobody else is entering, it will close. So basically there are some states, like usually it will be closed, and when somebody is near, it will sense that somebody is near and then it will open, and when it senses that nobody else is there, it will close. Right. So these are some examples of state-based devices, right? So these are some simple examples. I'm not going into the detail of why they are automata or why they are like automata, right? And the goal of studying finite automata is like as a precursor to seeing more complex models of computation that we will see later, right? So we'll first try to understand simpler models before going into more involved setups, right? So as I said, in the finite automata, the states are the main way that the machine keeps track of where it is and how, what it is supposed to be doing. So in a sense, the states function as the memory. Okay, so the memory, there is no extra memory apart from what is there in the states. So let's just see an example which will clarify things. So in finite automata itself, we'll first see the deterministic finite automata, right? So we'll see what is deterministic, what is finite about this automaton, so on, right? Right. So this is the deterministic finite automaton, right? So this is an example. So what do we see here? So there are 4 circles, Q1, Q2, Q3 and Q4. These 4 circles are states, okay? And the starting circle is Q1 because right, the starting circle is Q1. This is the starting circle because this is starting state because there is an arrow right next to it, right? So you see there is an arrow right next to it, so it's a starting state. So an arrow like this indicates a starting state, right? And so there are, if you see, for each state there are 2 outgoing arrows, one for 0 and one for 1. So Q1 outgoing arrow to Q3 for 0 and outgoing arrow to Q2 for 1, and Q3 outgoing arrow to Q3 outgoing arrow to Q4 for 0. I have missed to actually denote another outgoing arrow, so this should have been this, right? So there is this, the outgoing arrow actually comes back into Q3, right? So the outgoing arrow for 1, okay? So this is the 2 outgoing arrows for Q3. For Q2 and Q4, basically if you see 0 or 1, the arrows just go back to itself, right? So let's try to see what it does. Maybe it's simplest by, let's say, what happens when a string such as, let's say 0 1 1 is read by this machine. So what happens is the starting position is Q1. When it reaches 0, it moves to Q3. Okay, when it sees 0, it moves to Q3, and then when it sees 1, it remains at Q3, and when it sees the second one, it again remains at Q3. So after reading 0 1 1, it ends at Q3, right? So it goes like this. It first goes to Q1 and then to Q3 and then to Q3 and then to Q3 again. So starting at Q1, then goes to Q3 and then remains there, right? So this is what happens when it reads 0 1 1. It starts at Q1, so reading the 0, it goes to Q3, then reading the 1, it remains in Q3, and reading the 1, it remains at Q3 again. So at the end of reading 0 1 1, it remains at Q3. Now let's see 1 0 1. It starts at Q1. When it reads a 1, it moves to Q2, right? And when it reads a 0, it remains at Q2, and then it reads a 1, it remains at Q2 again. So in fact, once you reach Q2, you're stuck at Q2. You're not going to move out of Q2, right? Maybe another example, maybe 0 1 0. So you first 0 takes you to Q3, 1 keeps you at Q3, and then 0 again takes you to Q4. So I've taken 3 strings and told and shown where it ends, right? And the only thing that I have not described is the notion of accepting a certain string, right? We say that this machine accepts a certain string if it ends at a certain state, which is like this double circle. So in this case, the only state with a double circle is Q3. So double circle means it's an accepting state, right? So which means that this string gets accepted, 0 1 1, because it ends in Q3, while these two do not get accepted. Q2 0 1 0 1 and 0 1 0 do not get accepted, right? So it starts. So just to summarize this, it starts at Q1 the start state. I'm going to give the definition formally, but moves as per the arrows, right? So for instance, 101, it start with q1, then it moves to q2, then 0 it again remains at q2, and 1 it again remains at q2, right? So it moves as per the arrows and decides. So accept if ending at a state which has this double circle, right? So let's try to understand what are the strings that this machine accepts. What are all the strings? So we know two strings that are not accepted. 101 is not accepted because it ends in q2, and 1010 is not accepted because it ends in q4. So the only strings that are accepted are the ones that are ending in q3. So which are the strings that end in q3? Well, it's not that hard to see because it has to start at q1 and then move to q3. There is only one way to move to q3. The first symbol should be 0, right? And then after that, for it to remain in q3, it only has to see once. So the string must be of the form 0 followed by 1, 1, 1, 1, some number of ones. It could be no ones, right? Or it could be 1, 1, or it could be 2 ones, it could be 3 ones, or it could be 100 ones, right? Because if it sees a 0 again, it will move to q4. So the starting symbol must be 0, and then on it should only be once. So the set of strings that are accepted are 0, 0 followed by 1, 0 followed by 2 ones, 0 followed by 3 ones, and so on, right? So there are infinite number of strings possible, right? You could have 0 followed by 10 ones, 20 ones, 100 ones, 1000 ones. Everything is accepted by the by this deterministic finite automaton, right? Right. So I have given a brief, I have given an example and kind of explained which are the strings accepted. And we say that this set of strings that are accepted by this DFA is the language recognized by this DFA. Okay. So I will define everything formally and state all this formally once again, but this is just to give a informal picture. Okay. So why is it called deterministic? It's called deterministic because every state, if you are at q1 and see a if you are at q1 and you see a 0, you know exactly where you have to go. You have to go to q3. If you see a 1 at q1, you have to go to q2. So you know exactly where to go. So the movements are fixed if the string is fixed. So that's why it's called deterministic. So you may think of this as the natural thing to do, but later we will see models that do not have this property. Even if you see a 0 at a certain state, there could be multiple options, right? So that's why it's called deterministic. Every time when you see a certain symbol at a certain state, you know exactly what to do. That's why it's called deterministic, right? And finite because this picture here has 4 states. So in any deterministic finite automaton, the number of states should be finite, right? So that's why it's called finite. Let's try to understand by seeing a couple of more examples. So this one, let's see. There are only 2 states. Of course, the symbol is binary. So you can see what happens. The only strings that are accepted are those ending in Q2, and which are the ones that end in Q2. So let's try to see. So if the first symbol is 1, you move to Q2 and then you remain there. So the first symbol, so all the strings that have the first symbol 1 are accepted, but are those the only ones? Let's say the string 0, 1, 0. Does this get accepted? 0 keeps you at Q1, 1 takes you to Q2, and then once you move to Q2, you are accepted for sure. So this is accepted. Let's say, as I said earlier, 1, 0, 0 is accepted because from Q1 you immediately go to Q2, right? So Q1 is the starting state because it has this arrow by the left side. So any string that has a 1 seems to be accepted. So maybe another way to think about this, which are the strings that are not accepted? The strings that are not accepted are those that remain in Q1, because once you go to Q2, you are stuck at Q2 and you are accepted. So which are the strings that are not accepted? Those that remain in Q1. And which are how do you remain at Q1? If the string is only containing zeros. So if you contain only zeros, then 0 or 0, 0, 0, 0, 0, like some number of zeros. Because once you see a 1 at any point, you immediately move to Q2. And then you are accepted. So just to summarize, the set of strings accepted or language of the above is equal to all the strings that have at least one, because if you see, the only way to not get accepted is if you are a string of zeros. So anything that are not a string of zeros means if it has at least one, you move to Q2 and then you are accepted. Right? The first one that you see will take you to Q2. Now let's see another DFA. So the starting state is Q1 here, right? And let's see what happens. So let's try to see what this thing does. So whenever you see a 1, you move to Q2. Unlike the earlier DFA, once you move to Q2, you can come back to Q1 here, right? So whenever you see a 1, you come to Q2. Whenever you see a 0, you come to Q1. And if you see, what is happening is that regardless of whether you were at Q1 or Q2, regardless of where you were, if you see a 1, you move to Q2, right? If you see a 1 from Q1, you move to Q2. If you see a 1 from Q2, also you move to Q2. Regardless of where you are, if you see a 0, you move to Q1. So, in other words, let's consider two strings 0, 1, 0. So you are in Q1, 0 keeps you at Q1, 1 takes you to Q2, and 0 takes you back to Q1. It is not accepted. 1, 0, 1, for instance, first symbol is 1, the 1 takes you to Q2, the 0 takes you to Q1, and the 1 takes you to Q2 again. This is accepted. So 0, 1, 0 is not accepted, while as 1, 0, 1 is accepted. So now you may be seeing what is going on here, right? So for it to be accepted, you have to end in Q2. And how do you end in Q2? If the last symbol is 1, right? So the language all the strings that end in 1. Okay, all the strings that end in 1, because if you have to be accepted, you have to end in Q2, and to end in Q2, you have to end, the last symbol seen should be 1. Okay, this is quite similar. In fact, the movements, the transitions are exactly the same. The only difference is in the accepting state. Q1 and Q2 and the arrows are exactly the same, the labels are exactly the same. The only difference is Q1 is accepting here and Q2 is not accepting here. So now if you see anything that ends in Q1 is accepted, and it's not that difficult to see this. You can work out the reasoning yourself. The language is the set of all strings that end in 0, because in this picture, like if you see 1, 0, 1, so 1 takes you to Q2, 0 takes you to Q1, and 1 takes you back to Q2 and it is not accepted. Whereas 0 1 0, 0 keeps you at Q1, 1 takes you to Q2 and 0 takes you back to Q1. This is accepted. So anything that ends in 0 is accepted, right? So we have seen some examples but not the formal definition. So let's come to the formal definition. The formal definition of a DFA or a deterministic finite automaton is that it is a 5 tuple. Okay, so just a small warning before these definitions. So when you see 5 tuple with q, sigma, delta with all these Greek symbols, one may get a bit like overawed by this or scared by this. So don't be so scared. It's the concept is simple, which is why I decided to do the example before coming to the actual definition. The concept is fairly straightforward. This is just a way to like formalize this notion and make a formal definition, right? So it's more important that you understand what is going on than understanding this bunch of notations. Okay, if you understand the mechanics or what happens when a certain string is input to a certain finite automaton, that is more important than the definition itself. So it contains q, sigma, delta, q0 and f, right? So q is the set of states. So set of states is finite. Okay, so this set of states is finite, right? This is the definition of a deterministic finite automaton. So even in this picture we saw the set of states of all of these are finite, right? We didn't draw any infinite states thing. Sigma is the alphabet, right? In both the examples or in all the examples that we saw, the alphabet was 0 1. So we had arrows labeled 0 and 1, and the strings that we are dealing with were also 0 and 1, right? So the alphabet was always binary in the examples that we saw. So that is the alphabet. So that is, in this case, it is finite. So delta is a transition function. So delta, it takes two things. One is the q, the current state, and the next symbol that you are reading, and then what is the next state. So if you are in a certain state, let's say q1, right, and if you see a 0, this may say you go to q5. So in other words, this delta is saying delta of q1 0 is q5. If you are in q1 and see a 0, you move to q5. So that is pictorially depicted above and kind of notationally depicted as using the delta. And in the set of states, one state is designated as the start state, and that we call it q0. So I think in our examples, the start state was q1 here, here also q1, here also q1, here also q1. So we had q1, right? So we need a designated start state. It may be called q0, q1, whatever, but there has to be one designated start state. So there is an example right below where the start state is depicted with the letter, denoted with the letter S. And F is a set of accepting states, and F is a subset of states. So start state is a single state, and while F is a set of accepting states, right? So, but in all the examples that we have seen so far, the set of accepting states also has been a single. So here it's only q3, here it is just q2, here also it's q2, and here it is q1. So in all the examples that we have seen, the set of accepting states have been a single state, but you could have multiple states being accepted, right? So maybe let's try to see fit a picture to a definition. So this is yet another DFA, right? So how many states does it have? It has 5 states. There is a starting state S, then q1, q2, q3 and q4. There are 5 states: S, q1, q2, q3 and q4, right? So that is depicted here, right? And the alphabet, if you see the arrows are labeled with 0 and 1. So the alphabet is binary. So sigma is 0 and 1. And let's see the delta here. Delta S0 is Q1, delta S1 is Q3. Right, so that's, I've noted it here. Delta Q1 0, so if you see 0 at Q1, you come back to Q1. So delta Q1 0 is Q1, delta Q1 1 is Q2, right? Delta Q1 1 is Q2. Delta Q2 0 is, if you see 0 at Q2, you actually move to Q1. Delta Q2 1 is, you remain at Q2. Similarly, delta Q3 0 is Q4, and delta Q3 1 is Q3. And finally, delta Q4 0 is Q4, and Q4 1 is also Q3. Okay, so the delta is also defined, so you can verify this from the notes. The starting state is S, and here we have two accepting states, Q1 as well as Q3. So now let's try to understand what are the set of strings that are accepted by this deterministic finite automata. So one thing that we can see is that if the first symbol is 0, from S it comes to Q1. So let's try some examples. So let's say 0 1 0, is it accepted? First symbol is 0, you move from S to Q1, and then you see a 1, you move to Q2, and then you see a 0, you move to Q1 back, and which is an accepting state. So 0 1 0 is accepted. How about 0 1 1? From S you move to Q1, then you move to Q2 upon seeing the second one, and the third one keeps you at Q2, which is not accepted. So this is not. How about 1 0 1? From S you move to Q3, and then 0 takes you to Q4 and back to Q3. So this is accepted. How about 1 1 0? 1 takes you to Q3, 1 keeps you at Q3, and 0 takes you to Q4, which is not accepted. So now you may have understood what is going on. So what is happening is that the first symbol decides whether you move to the left part or the right part. If you move to the left part, by the left part what I mean is this part over here, then you remain at you go to Q1 if the last symbol seen is 0, or Q2 if the last symbol seen is 1, right? So what is happening is that to get into the left side you need to start with 0, and then to be accepted you need to end with 0, right? And to go to the right side you need to start with 1, and you need to start with 1, and to be accepted you also need to end with 1. Okay, so the language of this DFA is the set of all binary strings that start and end with 0, or start and end with 1. In other words, starting and ending with the same symbol. So that is the language of this DFA. The set of all strings that start and end in the same symbol. Let me ask you another question. This is something. Where will the empty string, so we also talked about an empty string which does not have, which has 0 length, will it be accepted by this machine, by this automaton? So the empty string is like it does not have any symbols. So the empty string will end at the starting state, which is in this case S, which is not an accepting state. So the empty string will not be accepted. And hence it is not part of the language. I am just saying this. We can go back and check a couple of other DFAs also. Here empty string is in the language, so because the starting state is where the empty string ends. So the language here is the strings that end in 0 union the empty string. Over here empty string is not accepted because the starting symbol is not, the starting state is not an accepting state. Same here also. So these two languages remain the same, whereas here the strings that end in 0 plus the empty string should be the language.